Welcome to the lecture series Time Value of Money, Concepts and Calculations. In this lecture, we will deal discrete annually compounding. Discrete compounding refers to the method by which interest is calculated and added to the principal at specific interval of time. For example, interest may be compounded daily, weekly, monthly or even yearly. The frequency at which interest is compounded has a slight effect on an investor's effective annual yield. With greater frequency of compounding, that is, as holding periods become smaller and smaller, the effective rate gradually increases, but in smaller amounts. Discrete compounding relates to measurable holding periods and a finite number of holding periods. For example, Mr. XY deposits his saving rupees 10,000 in a 2-year time deposit scheme of a bank which offers 8% interest compounded quarterly. What is the maturity value at the end of second year? Now, let us analyze this problem. Quarterly compounding means there are 4 compounding periods, 3 months each in a year. Instead of paying interest once in a year, it is paid in 4 equal installments after every 3 months. Using the above illustration, there will be 4 into 2 years, that is equal to 8 compounding periods, and the interest rate for each compounding period will be 2%, which will be calculated as 8% divided by compounding period in a year is equal to 8% divided by 4 is equal to 2%. Now, if you see this, if I see here periods, it starts with 0, then 1, 2, 3, 4, 5, 6, 7 and 8. So, 8 compounding periods, and if I see month wise, the first compounding period ends after 3 months, second after 6 months, third after 9 months, fourth after 12 months and fifth after 15 months, sixth after 18 months, seventh after 21 months and eighth after 24 months. And year wise, if we see, its starting year is 0, here is the first year and here is the second year. Now, if we calculate what will be the future value, the distance of between one period is 3 months, the 0 to 1 is 3 months, and so we are investing P amount at t equal to 0, and this amount grows to P into 1 plus 0.8 divided by 4 to the power 1 after the end of the first year. After the end of the second year, it is P into 1 plus 0.8 divided by 4 square, and in a similar manner at the end of 8th period, this is P into 1 plus 0.8 divided by 4 to the power 8. So, this is shown in the timeline. So, Mr. XY deposits the saving of 10,000 in a 2-year time period scheme with the bank which offers 8% annual compounded quarterly. What is the maturity value at the end of second year? So, we solve this. So, the interest period is 8 divided by 4 is equal to 2%. So, interest rate per period is 2%, which is 0.02, and we have 2 years and principal is 10,000. Now, if we calculate from the first principle, what will be the result. So, a period ends is 0, at 0 period we invest 10,000, which is the principal amount, interest per period is 0.02, amount of interest earned is 0 and beginning principal is 10,000 and period ending principal is 10,000, because at t equal to 0 obviously no interest will be earned, but at the end of that period, this is first period, after 3 months we have beginning amount 10,000, interest per period is 0.02. So, interest earned is 10,000 into 0.02 comes out to be 10,000 plus 200. So, period ending principal becomes 10,200 now, and this period ending principal will become the period start principal for second period, and again the 0.02 we earn 204 interest. So, my beginning principal is 10,200 and ending principal is 10,404. This will work as a starting value for the starting of the period 3. So, beginning amount of period 3 is 10,404, interest per period is 0.02, interest earned is 208.08. Now, this beginning principal was 10,404. So, the ending principal is 10,612.08. Similarly, for starting of the fourth period, this value which is 10,612.08 becomes the principal amount here, and interest rate is 0.02. So, interest earned is 212.24. Now, the final value becomes 10,824.32. Again this becomes the principal of the start of the fifth period, and the value grows to 11,040.81 at the end of the fifth period. So, it becomes the starting value at the start of the sixth period, and at the end of the sixth period this becomes 11,261.62. At the start of the seventh period this is 11,261.62, and the end of the seventh period it is 11,486.86. So, at the start of eighth period this is the principal amount 11,486.86, the interest per period is 0.02. So, the final value becomes 11,716.59. So, this is the amount which the bank will offer at the end of second year. So, what calculation method we showed just now is from first principles. Now, let us see what is discrete compound interest formula. In common industrial practice, the length of the discrete interest period is assumed to be 1 year, and the fixed interest rate I is based on 1 year. However, there are cases where other time units are employed. Even though the actual interest period is not 1 year, the interest rate is often expressed on annual basis. This we will always see, that 8% compounded quarterly, that 8% is 8% annually, and in such cases basically we express nominal interest rate R, and nominal interest rates are expressed always annually. Consider the example in which interest rate is 2% per period and the interest is compounded quarterly. So, a rate of this type would be referred as 2% compounded quarterly. Now, IPR, that is interest rate per period, is equal to the nominal interest rate divided by the number of periods. So, the interest rate given as 8% per annum compounded quarterly, that 8% comes from 2% into 4, which becomes 8%. So, in such cases we will find that invariably normal interest rates R is given, which reads like 8% per annum compounded quarterly. The R is nominal rate compounded n times per year. The interest rate is R by M and the amount Sn or Fb at the end of 1 year or n years as the case may be is given by Sn is equal to P0, Sn is the final value of the sum P0, P0 is the principal amount or present value in brackets 1 plus R by M brackets close to the power M. This is when I am calculating the Sn value, which is the final value for 1 year, and this is equation 1. Sn equal to P0 1 plus R2 divided by M whole to the power Mn is the value of Sn, which is the final value for n years when it is compounded m times per year. Now, take a problem. We are solving it with equations. First, we have given example 1, which is Mr. X deposits saving 10,000 in 2 years time deposit scheme of a bank which offers 8% per annum compounded quarterly. What is the maturity value at the end of 2 years? This problem was solved earlier using very fundamental concept. Here we will solve the same problem using formula which we saw just now. The solution is R is 8%, which is nominal interest rate, P is rupees 10,000, N is 2 and M is 4 because it is quarterly compounded. So, if we use this formula Sn is equal to P0 1 plus R divided by M to the power Mn, then Sn or Fb is equal to 10,000 1 plus 0.08, which is the nominal interest rate, and M is 4 here because quarterly compounding, to the power 4 into 2, which comes out to be 11,716.59. It should be noted that the result rupees 11,716.59 obtained from the above problem using first principle and that of the equation 2 are the same, and hence it can be concluded that equation 2 is correct. Now, let us see what type of problems can be created for the discrete compound interest, and we call it as a problem matrix. Now, the problem matrix can be generated from the equation 2, this S is equal to P into 1 plus R by M to the power Mn. Now, if we analyze the unknowns and variables, so we find that it is one equation and hence one unknown can be solved using this one equation. Further, the above equation which contains 5 variables, and what are those 5 variables? S, P, R, M and N, can be solved to find out the value of a single unknown variable only when other 4 variables are known. Thus, 5 types of problem can be generated out of this equation. The problem matrix for the above equation is shown in the next slide. This is our problem matrix. Now, the first type of problem which I call problem A, in the problem A, P, R, M and N are given and we have to find out the value of S, and the formula which will be S is equal to P in brackets 1 plus R divided by M whole to the power M n. And what type of problem this is? That future value S has to be found out when present value P, interest rate R, frequency of compounding per year M and number of years N of compounding are known. If we come across such type of problem, we will call it a problem A. Now, for the second type of problem, the given is S, R, M and N, and we have to find out what is the value of P. So, P is equal to S divided by in brackets 1 plus r divided by m to the power n into m. In this problem, we have to find out the present value of p where s, r, m and n are known, and we will call this type of problem B. Now, if you see the third type of problem, in the third type of problem S, N, P and M are given, and we have to find out R, which is the interest rate, nominal interest rate, and we can calculate this by the formula R is equal to M in brackets S by P to the power 1 by M n minus 1. In this case, we have to find out the interest rate R, where S, N, P and M are known, and such type of problems will be called problem C. The fourth type of problem is when S, P, M and R are given, and we have to find out N. So, we will use the formula N is equal to ln S by P divided by M into ln 1 plus R. In this case, we have to find out the number of years n when S, P, M and R are known. Such type of problems will be called problem D. Now, the fifth type of problem is where S, P, R and N are given, and we have to find out the value of M. The formula here will be S by P to the power 1 by M n minus 1 is equal to R by M. So, here we have to determine the value of M, the frequency of compounding per year when S, P, N and R are known. The value of M can be determined using trial and error method, because we will find that in the left hand side there is M and in the right hand side there is M. So, we have to use trial and error method to solve this problem and to calculate M, and such type of problem will be designated as problem E. What conclusion we derived out of this? The conclusion of number 1, under an annual interest R, the annual compounding money in a bank account will grow with a multiplier 1 plus R each year. Number 2, if compounding occurs m times per year, the multiplier for each compounding at the end of the period will be 1 plus R by M. And third conclusion is to find out the final value of amount compounding m times per year for n years. Following equation should be used: Sn or Fv is equal to P0 in brackets 1 plus R divided by M whole to the power m into n. Fourth conclusion, to convert annual compounding to discrete compounding, change R to R by M and N to M into N as shown below. So, the first formula, which is simple compounding or annually compounding, is Fv is equal to 1 plus R to the power n, but if I go for discrete compounding, the Fv will be 1 plus R divided by M and whole power m into n. So, what I am doing, R is changed to R by M and M is changed to M into N. Now, let us see what is the value of M, that is compounding frequency, when different time periods are decided. In a discrete compounding problem, the value of M may vary widely depending on frequency of compounding. So, M is equal to 1 when yearly compounding is used. When M is equal to 2, semi annually compounding is used. When M is equal to 4, quarterly compounding is used. When M equal to 12, monthly compounding is used, or other way we can say, for monthly compounding M is equal to 12 or quarterly compounding m is equal to 4. For daily compounding m assumes a value of 365, for hourly compounding m assumes a value of 8736, and for compounding per minute the m has a value of 5,24,160. Now, let us see the effect of the discrete compounding factor, that is 1 by r by m to the power m, on different values of m and nominal interest rates. Now, suppose r is 5, which is the nominal interest rate per year, and for this value r equal to 5%, if I am doing annually compounding, then my discrete compound factor, which is given by 1 plus r divided by m to the power m, becomes 1.05. For semi annually, when m value is 2, it is 1.050625. When it is quarterly, that is m equal to 4, it is 1.050945, and what is monthly 12, m is equal to 12, it is 1.051162. When it is daily, that is m is 365, it is 1.051267, and when it is hourly 8760, it is 1.051271, and what is minutely, that means each minute it is compounding, and m is equal to 524160, this is 1.051271. What indication it gives? That when frequency is increasing, the factor is not changing much. For example, when m is equal to 8760 and m is equal to 524160, the value of discrete compounding factor, which is 1 plus r by m to the power m, becomes almost same up to say 6 digit. So, what we find that after certain amount of frequency, this factor does not change much. The similar conclusions can be found out for r equal to 8%, r is equal to 10% and r equal to 20%. We see that for hourly and minutely compounding, the values are almost same for all nominal interest values, whether it is 5%, whether it is 8%, whether it is 10% or whether it is 20%. Let us take problems now. Problem type A. This is example 2. If rupees 10,000 were loaned for a total time of 1 year at nominal interest rate of 18% per year, compounded monthly, then find the future value of amount after 1 year. Now, let us analyze this problem. In this problem, P is given, that is rupees 10,000, our nominal interest rate is given 0.18, that is 18%, n is equal to 1 and m is equal to 12, as the compounding is monthly and there are 12 months in a year, and what is demanded is the future value. So, I can use my future value equation. Future value is equal to P into 1 plus r by m to the power m n, that is 10,000 into 1 plus 0.18 divided by 12 in brackets to the power 12 into 1, which becomes rupees 11956.18. That means, if I invest rupees 1000 with 18% interest rate compounded monthly, then it will convert into 11956.18. However, you will find that this value will be always more if compounding is used for yearly. Now, let us take a mixed problem, which is example 3. For the case of nominal annual interest rate of 20% per year, determine part A, the total amount to which rupees 1 of initial principal would accumulate after 1 year with annual compounding and the effective interest rate. Part B, the total amount to which rupees 1 of initial principal will accumulate after 1 year with monthly compounding and the effective interest rate. Part C, the total amount to which rupees 1 of initial principal would accumulate after 1 year with daily compounding and the effective annual interest rate. Number D, the total amount to which rupees 1 of initial principal would accumulate after 1 year with hourly compounding and the effective annual interest rate. Now, here if we see what we are doing, that the time period is being changed. In part A, time period is 1 year, in part A it is the compounding is monthly, in C it is daily, and in D it is hourly. And then we are also asking to calculate the effective interest rate, which will give us a feeling that how this effective interest rate increases when frequency of compounding per year is increased, but it asymptotically remains constant. Now, for answer part A, P 0 is the principal, which is rupees 1, N is equal to 1, R is equal to I, and I effective is 0.2 or 20%, because for annual compounding R is equal to I and I is equal to I effective, and that is why R is equal to I effective is equal to 0.2 or 20%. But Sn, that is the final value, is P 0 1 plus I effective to the power n is equal to 1 into 0.02 to the power 1 is equal to 1.2. Now, this Sn can be found out in different way. I can replace I is equal to R is equal to I effective for annual compounding, but part B the things will change. For part B, P 0 is equal to 1, R is equal to 0.20, M is equal to 12 and N is equal to 1. So, I have to use this formula, Sn is equal to P 0 in brackets 1 plus R divided by M to the power M. So, Sn is equal to P 0 into 1 plus R divided by M in the whole bracket to the power M is equal to 1.2194. So, what we saw that if it is annually compounding, the Sn value is only 1.2. When it is monthly compounding, the value rises to 1.2194. So, slight rise in the value. So, any guy who is doing this will get more money. Now, in part C, P 0 is equal to 1, R equal to 0.20, N equal to 1 and M is equal to 365. Here compounding is daily. So, Sn is equal to P into 1 plus R by M whole to the power M comes out to be rupees 1.2213. Now, this is 1.2213 is more than rupees 12194, and hence when I increase the frequency of compounding by compounding it daily, then my money Sn value, that is final value, increases slightly. And I effective is equal to, this is the formula of I effective, 1 plus R by M whole to the power M minus 1. So, comes out to be 0.2213. That means that the I effective has also increased than the R value if frequency of compounding is increasing. For part T, P 0 is equal to 1, R 0 is equal to 0.20, N equal to 1 and M is 8760 because it is hourly compounding, and I effective is equal to 0.2213999. So, here we see that up to 4 digit it is matching with the daily compounding. So, I effective has not increased much when the frequency has gone beyond daily to hourly, and Sn is equal to 1.221399. Let us take the problem type A. This is example 4. If rupees 1000 were loaned for a total time of 1 year at nominal interest rate of 24% per year compounded monthly, then find the future value amount after 1 year. Or if 1000 were loaned for a total time of 1 year at a monthly interest rate of 2%, then find the future value amount after 1 year. Now, in the second part of the problem it is monthly interest rate is given, and in the first part of the problem 24% per year compounded monthly is a nominal interest rate is given. So, we should not confuse here. So, the nominal interest rate is IPER, that is per period interest rate into number of periods, that is 12. So, R it comes out to be 24% per year. So, Sn is equal to P 0 1 plus R divided by m to the power m, because n here is 1. So, m into 1. So, that is why we have written m, because the compounding is for 1 year, but compounding monthly. So, m is equal to 12, Sn is equal to 1000, 1 plus 0.24 divided by 12 whole to the power 12 is equal to 1268.5. That means, if I invest rupees 1000 for 1 year with a nominal interest rate of 24%, then after 1 year it will convert into 1268.5 when it is compounded monthly, and this value will be more than the value of Sn if it is only compounded yearly. Let us take a mixed type of problem, which is example 5. For a nominal interest rate of 18% per year, compute for a principal of 1000 what will be the final amount after 1 year of annual compounding. Also find the effective annual interest rate. Part B, for a principal of 1000 what will be the final amount after 1 year with monthly compounding and also effective annual interest rate. Part C, for the same principal of 1000 find out the final amount after 1 year when daily compounding is used, and also find out the effective interest rate. Here also we are finding the final value when frequency of compounding is changing, and at the same time is also finding out the effective annual interest rate, which gives you a feel that your final value will increase with number of compound when number of the frequency of compounding is increasing. Now, the solution is for part A, P is equal to rupees 1000, R is equal to 0.18, N is equal to 1. In this case R is equal to I effective is equal to 0.18, because for yearly compounding R is equal to I effective equal to I. So, final amount FB is equal to P into 1 plus I to the power 1, or P equal to 1 plus I effective to the power 1, it comes out to be 1180. For part B, P is equal to 1000, R is equal to 0.18, M is equal to 12. So, FV is equal to 1 plus R by divided by M whole to the power M. This is 1000, 1 plus 0.18 divided by 12 whole to the power 12 comes out to be 1195.62. So, here we see very clearly that when compounding is yearly, my final value is 1180, and when compounding is monthly, my final value is 1195.62. That means, it has increased when my compounding period has increased. So, I effective will also increase, because I effective is a parameter which shows whether the compounded value will be more or less. So, I effective is equal to 1 plus R by M to the power M minus 1, it comes out to be 19.65%. Now, this percentage is more than the R value of 18% nominal interest rate. It shows clearly that if I am increasing the frequency of compounding, the FB value will increase. Now, for part C, P is equal to rupees 1000, R is equal to 0.18 and M is equal to 365. So, now in the frequency has increased to daily compounding. So, FB is equal to 1 plus R by M to the power M, which comes out to be rupees 1197.16. So, we see that further the FB value has increased, and so the I effective will also increase, and I effective has become 19.72. Now, if we see here the monthly compounding and daily compounding, the I effective value has not changed much. only of the tune of say 0.2% or so. But if you see from yearly compounding to monthly compounding, it has changed by 1.56%. So, when we increase number that is compounding frequency, the differential increase in I effective becomes lower and lower and assumes a asymptotic value. Let us take another example, which is example 6. If Mr. XS pays 5.12 nominal interest compounded quarterly, what is the effective annual interest rate? So, the problem here is very clear. If somebody is clever, he can pick up the results very quickly. The nominal interest rate is 5.12 and compounded quarterly. So, the effective interest rate will be slightly more than 5.12 and that we will observe here. So, results are A 5.219%, B 7.250%, C 9.893% and D is 12.552%. Now, solution I effective is, this is the formula of I effective, 1 plus R by M whole to the power M minus 1 comes out to be 5.2191%. So, we see that this is little bit higher than the nominal interest rate. So, any answer which is very close to nominal interest rate or it is not very different than the nominal interest will be the correct answer. Now, let us see the problem type C. Example 7. 10 years ago, rupees 10,000 was deposited in a bank account and today it is worth 22,595. The bank pays interest semi-annually. What was the nominal annual interest rate paid on this account? So, what is available and what is demanded is P is given 10,000, S is given 22,595, M is given 2 because it is semi annually, that means in a year 2 times, N is equal to 10. So, what is R? So, here we see that the formula S is equal to P 1 plus R divided by M to the power M n. So, here 22595 is equal to 10,000 1 plus R by 2 whole to the power 2 into 10. So, we have to find out the value of R. So, if we solve this equation, then it is 1 plus R by 2 is equal to 2.2595 to the power 0.05 and R comes out to be, by solving, comes out to be 8.32%. So, obviously, your answer D is correct. Now, let us take another problem, which is problem type B, example number 8. 5 years ago, a certain sum of money was deposited in a bank account and today it is worth 10,775. The bank pays 6% nominal interest compounded quarterly. What was the amount of money deposited? Solution: S, that is PB is FB is given as 10,775, M is given as 4 because it is quarterly. So, quarterly compounded M is 4, number of years N is given 5, R is given 6%. Now, question is what is the value of P? So, we have this equation S is equal to P in brackets 1 plus R by M whole to the power M into N. So, if we put this values into this, 10775 is equal to P into 1 plus 0.06 divided by 4 to the power 4 into 5. So, which comes out to be P into 1.346855 or P is equal to 8000.12. So, if I spend 8000 rupees, it will grow to 10,775 if the interest rate, nominal interest rate is 6% and if the compounding is quarterly. Now, let us the problem type D, an example number 9. Some years ago, rupees 7,000 was deposited in a bank account and today it is worth 11,259. The bank pays 8% nominal interest compounded quarterly. For how many years the money was invested? Now, if we analyze this problem, the given is P is equal to 7,000, S is equal to 11,259, R is equal to 8%, M is equal to 4, and what is the value of N? N is unknown. So, 4 values are known, 4 variables are known and fifth variable is unknown. So, we can solve because we have one equation. So, this is 11259 is equal to 7,000 into 1 plus 0.08 divided by 4 to the power 4 into n. So, 4 into n, if I take the log, 4 into n is equal to ln 11259 divided by 7,000. Now, whole divided by ln 1.02. So, if we solve this, then 4 n is equal to 23.9997 and n is equal to 23.99969 divided by 4, which comes out to be 5.999 and which is approximately equal to 6 years. Now, problem type E, example 10. 5 years ago rupees 9,000 was deposited in a bank account and today it is worth 14091.13. The bank pays 9% nominal interest compounded for an unknown frequency per year. Find the value of the frequency of compounding per year. Now, the same equation S equal to P in brackets 1 plus R by M to the power m n. Now, the solution, what is given and what is required, let us see. P is given 9,000, S is given 14091.13, R is given 9%, M is not given and N is given 5. So, P, S, R and N is available and we have to find out what is the value of N. Now, if you remember in the first part of this lecture I have told you that when we find out M, it is a trial and error process, because left hand side contains M and right hand side also contains M. So, we have to go through a trial and error process. So, we can write down using this equation 14091.13 equal to 9,000 in brackets 1 plus 0.09 divided by M to the power M into 5. So, we convert it into two parts, that is 1.0.09 by M to the power 5 M is equal to 1.565681. So, let M is equal to 4, then LHS is equal to 1.5605 and RHS is equal to 1.565681. When M is equal to 10, LHS is equal to 1.565158 and RHS is equal to 1.565681, and for M equal to 12, LHS becomes equal to 1.565681 because RHS remains constant. So, when we are changing M, the LHS is changing. Now, for M equal to 12, the LHS has become equal to RHS, that is right hand side, LHS is left hand side becomes equal to right hand side. So, as at M equal to 12, LHS equal to RHS, the assumed value is correct. Thank you.